How does YouTube decide what videos to show you? The algorithm. Think of how Spotify chooses the next song in a playlist, or Netflix recommends the next show to watch, or Amazon shows you related products. Recommender systems are used by capitalist fat cats to keep you consuming their content to distract you from how unfair the world is and avoid you casting off the shackles of oppression and rebelling against your captors. Today we're going to learn how to make one. We are going to make a movie recommender system. We have the IMDb ratings for a bunch of users for different movies that they've reviewed. You can see that Michael Patrick Porkins rated The Godfather 2.5 out of 5, and Taffy Lee Fubbins rated Aladdin 5 out of 5. How do we use this to determine which other movies a user might like? Let's think of a way to make this problem simpler. Imagine if every user had already watched and rated every movie ever made. Then this would be easy. We'd just pick the movie with the highest rating. So another way of thinking about this problem is, can we create a model that predicts user ratings for movies they haven't seen? We basically want to fill in the gaps in the table, which is why this is called matrix completion. How do we do that? Again, let's try to make this simpler. Let's imagine we can boil down any movie to 3 important characteristics. They might be actionness, romance, and comedy. So Lord of the Rings would be a lot of action, a bit of romance when Eowyn is thirsting for Aragorn, but low on comedy. The Arnold Schwarzenegger and Emma Thompson classic Jr. has it all. High scores across the board. We've essentially compressed the entire complexity of the film industry into 3 numbers. And when we do this kind of compression of information in machine learning, we call it an embedding. So we can call these 3 numbers a movie embedding. And this choice is just an example. We could have equally picked length, budget, and Oscar-worthiness, or any other 3 attributes. And it doesn't even have to be 3. Our embedding size can be as big or small as we want it. In this example, we'll stick to these 3 to illustrate the point, but we'll come back to this idea later. That was a movie embedding. We can apply the same idea to a user embedding. For any given user, we could describe in 3 numbers how much they like action films, how much they like romance films, and how much they like comedy films. And for now, let's just pretend that we have these embeddings for every user and every movie. The process to decide how much a user would like a movie is just to see how similar the user and movie embeddings are. Uncle Jagdish loves action and hates comedy and romance, so if we show him an action-heavy movie with no comedy or romance, we get a high score. Multiply the action numbers together, then the romance numbers together, then the comedy numbers together, and add those up. The bigger the number, the closer the match. This single number acts as a predicted rating. If there's a movie with action but also comedy, it'll get a lower score, but kind of medium. And if there's a movie with no action but lots of romance and comedy, it'll get a terrible score. This process is called taking the dot product of 2 embedding vectors. We can repeat this for every movie to get the predicted rating, and then recommend Uncle Jagdish the movies with the highest match for him. Job done, thanks for watching. But wait, how do we get those embeddings? We just let the model learn it. I'll demonstrate this in the most sophisticated deep learning software of all, a spreadsheet. We're going to put 3 numbers next to each movie and 3 numbers next to each user. These are the embeddings, and to start with, they'll just be completely random numbers. If we take the dot product, it gives us the predicted score for any user-movie combination. So this table tells us our predicted ratings. And to start with, it's pretty rubbish, since the embeddings are random and we haven't trained it. We know the actual ratings that some users gave some movies, so for these known cases, our model should match the rating the user gave. We can calculate the differences between each of the actual ratings and our predicted ratings to give a crappiness score for each prediction. And then we add these all up for a single overall crappiness score called a loss. This is a single number that encapsulates, overall, how far apart are the model's predicted ratings from the ratings the users actually gave. Then we can twiddle the embedding knobs up and down until we get a combination that gives us the lowest loss. Now, I could twiddle my knob until I'm blue in the face, and on one long, hot, glorious day in the summer of 2014, I did just that. But to speed things up, Excel has a solver to automate the twiddling, which I'll do now. I define the cell that has my loss value. I want to minimize this. I define the cells that have my variables. These are the cells that Excel will twiddle to try to minimize the loss. These are my embedding values that are shaded in pink. And then I let the solver do its thing. Done. The model is trained and we have our embeddings. The embedding weights have been tuned, so our model now gives a predicted rating for any user-movie combination. Denny Doo Dinkins hasn't seen Star Wars Episode 6. According to our model, he would rate this a 4.8 out of 5, so this would be a good recommendation for him. So if we want to pick a movie to recommend to a user, we look at their row and pick the movie with the highest predicted rating. And that's it. Let's recap what we did. In this approach, we had an incomplete matrix of user ratings for movies, and we wanted to fill in the gaps. We introduced embedding values for each user and movie to encode some key attributes. Then we trained those embeddings to give us predicted ratings. This is what the grown-ups call probabilistic matrix factorization. And now you know how it works. So let the algorithm know that this video is premium shit by smashing that like button and subscribing. You might be saying, why did you do this in a spreadsheet? Why didn't you do this in Python so I can steal your code? And I would say,
why don't you go and f off then?
Nah, not really. That's actually a valid question and I'm glad you asked. It's actually really easy now that you know how it works. I've got a notebook here that's linked in the description that you can play with. We load the IMDb data in Python. We define a collaborative filter model, which starts with some random weights, just like our spreadsheet did. We pass it our data, and then we train it, which is just twiddling those embeddings like we did in Excel. And that's it. One more thing I said I'd come back to.
One more thing!
We should take a second look at these embeddings. You might wonder, how does the model know what the important characteristics are? We talked about action, comedy, and romance. How does the model know about these three things? In reality, it doesn't actually learn these three particular properties. It just learns three characteristics that separate the data most effectively. We can plot the embedding space to see what this looks like. We can also look more closely at the highest and lowest values of each embedding. So if we take the first embedding dimension, the movies with a low value are all cult classic films, whereas those with a high value are all kind of trash. There's a lot of Will Smith movies here. So embedding 1 might correspond to trashiness. Looking at embedding 2, movies with a low value tend to be more adult or higher age rating films, whereas those with a high value are more family-friendly movies. So embedding 2 corresponds to family friendliness. And similarly for embedding 3, a high value here seems to correspond to critically acclaimed films. This is a crucial point. We don't tell the model ahead of time what characteristics to learn. We just train it, and then after the fact, we can look at the values it's learned and assign some source of human interpretation to it. This is why when you look at the genres that Spotify or Netflix use, they can seem oddly specific, like deep melodic death metal, electroacoustic improvisation, Japanese jazz tronica, Nintendo core. They can use hundreds or even thousands of embeddings, and then it's just some guy eyeballing them and seeing what they look like. Okay, job done for real this time. Time to update your CV.